So hello everyone. Um, Hello everyone. My name is Mohammed Saad Nawaz. I am Secretary of the IEEE Computer Society Germany section chapter, and I will be moderating today's webinar. We have with us Dr. K.P.N Jayasena, who will be introducing this topic today. And so just for your information, this session will be recorded. The recording will be available later on to view. And for the questions, we will leave the last 15 minutes of the webinar for questions and answers. You can write your questions in the chat, or you can raise your hands and ask your questions at the end. The webinar has a couple of, so to say, feedback points. Apart from it, it is the wish of the speaker that we take the questions and answers at the end of the webinar. The stage is over to you, K.P.N, please.
Okay. First of all, I just want to check whether that I'm audible. Am I audible?
Yes.
Yes.
Yes. Yes,
And
you're
then
audible.
can you see my screen?
Yes.
Okay. Okay, I hope now you can see my screen. Yes. Okay, so then shall I start?
Yes, please.
Yes.
You can start
Okay.
now.
Okay. Good afternoon, everyone. I'm Dr. K.P.N Jayasena. So Mohammed mentioned previously, a postdoctoral researcher here at Technical University of Dresden. Today we are exploring a critical intersection in computer security, how this confidential computing and federated learning are transforming security in distributed systems. So this presentation actually I will take 45 minutes, and after that we will follow with some question and answer sessions. So we will journey from identifying fundamental security gaps in today's data driven world to presenting this one to the practical solutions that are being deployed in real healthcare and financial systems right now. So before we begin, I want to think about this. So every day that you are dealing with your personal data, and this data is processed on your servers, so you will never see it. By administrators, you will never meet. In countries, different countries, it's governed by laws, you may not understand it. So by the end of this talk, you will understand how we can change that framework, new milestones entirely. Okay, so today's presentation that I'm going to discuss about this exploring the future of confidential computing and federated learning. So advance in security in distributed systems. Okay, so today's roadmap for problem in solution space. So first we start with the challenge. Why traditional security is insufficient for modern distributed systems? Multi-party computations, cross-border data sharing, and sensitive edge devices. And then I'm going to discuss about the confidential computing. Some may know about this term. Okay, some may know about this Intel SGS machine, AMD SZV, ARM Trustone, and how these trusted execution environment create new security frameworks. And then I'm going to discuss about the federated learning. Okay, so that the new era of machine learning. So federated learning. So its promise of privacy, but also there are some vulnerabilities like inference attack, model positioning. Okay, so later we will discuss more about this stuff. What are the disadvantages in federated learning? Okay, and then the core idea in here, introducing this confidential federated learning. Okay, so leveraging from the confidential compute into the secure federated learning. Okay, how this kind of framework that we can make. Okay, and then we'll discuss more about the scenario based workthroughs of the architecture and protections. Okay, finally we'll wrap up with some future directions, research questions. Okay, so there are some research challenges in there, performance wise, standardizations, scalability. There are a lot of problems there. So finally we will have time for the identify some of your questions and insight and how we can adapt it into the real world deployment. Okay, so that's the today's agenda. And before moving on to the discussion about the technical things, okay, I just want to get your idea about this before diving into the technical details. So first, let's understand your perspective. Okay, so please scan this QR code, okay, and share one word that's come to your mind. When do you think about data security? Okay, so you can scan this one, or you can go to the menti.com using this QR code, this is code number. Okay, so then after that, I will present it. Okay, so I hope now you can see this screen. One word that comes to your mind when you think about this data security. Okay, so I can see the compliance, leaks, risks, hackers, privacy, yes, exploitations, afterthought, yes. So I can see a lot of words like privacy, trust. Okay, so those kind of meaning of these things are there. Risk. Yes, so these responses actually it helped me to tailor the examples throughout this presentation. So I can notice many responses that it is focused on the protections mechanism, privacy, uh, regulations. Okay, uh, that there are some challenges also we are going to address today. So security in data, so while it is being actively used. Okay, so without taking much time, we will move on to the again the presentation. Give me a time. Okay, I hope now you can see my screen. Okay.
No, not yet.
Not yet. Okay. It's connected. I hope now. Okay.
Yes.
Yes. Okay. So this slide, the scale of the challenge and unprecedented data explosion. So this slide sets the stage of showing the magnitude of the data explosion. Okay, so I will emphasize that by in 2025, okay, IDC Global Data Sphere forecast that they mentions that we are looking at 181 zettabytes numbers, so massive that they are almost unimaginable. Okay, and most of the data you can see it is unstructured, okay, making it hard to secure and analyze effectively. So on the left side I highlighted the rapid space. Okay, so petabyte of data every seconds, 3.81 petabyte every second generated globally. Okay, and also and most of the world data created in just the last 22 years, so 90% of the data created in last 2 years, and data doubles every 2 years, and 90% is unstructured. And also you can see in the right of the side, okay, so on the right I draw the attention to where this data is going: the cloud and internet of things. 100 zettabyte in cloud by 2025, and cloud market from 103 by 2029, 90 zettabyte from IoT devices. So over half will reside in the cloud and IoT devices. Okay, alone it generated 90 zettabytes. So the big message in here that I want to give in to you is there's a sheer scale and complexity of data growth. And security is not an optional, it is absolutely imperative. It's really, really important now when we are dealing with this much of data. Okay, so now the security crisis, the critical data in use protection gap. Traditionally, normally that they protect data in at rest. So that means when we are storing the data, that we will focus on the data at rest is encrypted on the disk, it's protected. Okay, so traditional security protect data at rest and data at transit, but there's a critical blind spot is there. Okay, so data it transmit is encrypted over a network, so you may know about this TLS, MLTS. Okay, when the data is transferred from one end to another end, so that communication path also encrypted, but there's a bottleneck in this data in use. Okay, so this data is actively processed in memory, completely exposed, the so accessible, so any privileged insider, operating system hypervisor, or compromised cloud admin, okay, that can access it. Okay, so this takes a huge cybercrime cost. Okay, so you can see 10.5 trillion projected there are cybercrime cost by 2025, and these are the some of the economical fact and the key security states. Okay, so there's a critical vulnerability. Okay, so green protects, these are the protector states, and the big red warn info in this in use data. Okay, so this gap is exactly why confidential computing is essential. So confidential computing is it's secure data while even it's being processed. Okay, closing the most dangerous exposures. Okay, so we will move on to the discussion about that. Okay, so the in today's discussion that I'm going to get two pillars: pillar 1 confidential computing and the pillar 2 as federated learning. So I will introduce our two pillars to solving this fundamental problem. Pillar 1 confidential computing. Okay, so it's protect data during the computation using hardware based trusted execution environment. protects data during the computation using this hardware-based TEs, trusted execution environment. So think of this as a creating cryptographically sealed wallet, okay, inside your processor where computation occurred. So market validation shows projected growth exceeding 40%, okay, CAGR through 2030. So this is not experimental technology, it is entire in mainstream adoption. So pillar 2 is the federated learning. So we will discuss it more later, that the federated learning, it means the collaboratively AI training without centralizing the raw data. Okay, so instead of sending data to the models, we send models to the data. Okay, so actually this is directly supported GDPR and data compliance, okay, requirement. So the key insight of this is combining these achieve, okay, confidential computing plus federated learning, that together can be enabled secure collaborative computation on distributed sensitive data sets. Okay, so now we will going to discuss more about this concept. So again, confidential computing. So those who are not aware of this one, I will explain what that means. Okay, data normally that the data security triangle is there. So traditional cloud protection address two vertices: data at rest, so that means encrypted storage, databases, data centers, and data in transit using TLS, encrypted networks, secure communications. Data in use, data in transit. And the third vertex is the data in use, remain unprotected. Okay, so normally, so this includes data being processed in memory, active computations, and runtime execution. So this is the new protection layer. So you can see in here, in the purple present, in your traditional cloud protections and new protection layer, processing, memory, and the execution. Okay, so this is not just another security feature, it is the paradigm shift. Previously, you had to trust the entire software stack, operating system, hypervisor, cloud provider, system administrator. Okay, previously we trust. So with confidential computing, your trust boundary is shrink to the hardware manufacturer and your own application code. Okay, so in here, the data is protected in use in the processing and the memory execution. So then there's another very important one. It's coming when we are discussing about this confidential computing, that is trusted execution environment. So trusted execution environment. So what is this trusted execution environment? Actually, it is a secure area within the processor with high-level security for code execution and data protection. So what are the key capabilities that include in the trusted execution environment? So it protection against some software attacks, even if the operating system, drivers, BIOS, and the are compromised. So your application runs in an encrypted memory region. So actually that even the kernel cannot access. So the protection for secrets even when attacker have full platform control. This trusted execution environment maintains confidentiality, integrity, okay, through the hardware enforced isolation. Hardware enforced isolation is there. Hardware based attestation capabilities is need to measure and verify the code and data signatures. Attestation, we should have to attest it whether we are running verify the code and the data signatures. So this enable them the remote parties to cryptographically verify that what code is running before sending sensitive data. So in here you can see in this uh, in this diagram, okay, shows how applications run in secure enclave. Okay, so these are the applications, operating system, virtual machine, so the hardware, Intel SGS. Okay, how application run in the secure enclaves, completely isolated from main memory and privileged system components. And notice this secure enclave boundaries, even with the root access, attack cannot penetrate these hardware enforced barriers. Okay, so this is the provide an option for hardware based attestation and verified valid code and data signatures. So that's the idea behind in this trusted execution environment. So then there's another thing, it's coming, why do we need confidential computing? Okay, so higher value of workloads, in the previous slides also that we discussed it, higher value workloads require security guarantees around the processing. There are a lot of personal identifiable informations are there. Government confidential informations are processing. High value assets are there. So cloud providers already have many programs. They are customers, why they should be trusted. So confidential computing based cloud framework, that this is the rising framework for trusting cloud providers with customer secrets. Okay, so cloud providers recognize this need. Therefore, they have extensive trust programs, but confidential computing shift from trust us to don't trust us, verify cryptographically. So this address the rising concern about trusting cloud providers with critical secrets. There are a number of cloud service providers nowadays offering this trusted execution based confidential computing today. Okay, so in here, uh, in this diagram that it's explained about what is the problem with data. I would be happy to share this sensitive data in the encrypted form if I know what the service provider is going to do that. So confidential computing will help dive more data to the cloud to enable more collaborations on sensitive data, aided by hardware processors. And confidential computing, you can say, it help to deliver privacy of the data, confidentiality for cloud platforms, and integrity for machine learning. So hardware enable confidential computing. So there are maybe some of them may know about this stuff, Intel SGS and the TDS. So those are the Intel provides two complementary technologies. SGS offers process level isolations and for individual applications. Think in securing a single database query. TDS provide VM level isolations for entire workload. So SGS has memory limitations but extremely strong isolations, and TDS scale better with broader trust boundaries. When we come to the ARM that it confidential compute architecture, it extend trusted execution capabilities to the mobile and edge devices. This is CC, and when we come to the AMD secure encrypted virtualization. Okay, so this approach focuses on entire VM encryption with secure nested paging. So SCV SNP provides strong memory encryption and integrity for complete virtual machines. And nowadays there are NVIDIA that the confidential GPUs also available. So you can see H100 architecture. It's provide confidential computing GPU memory for AI workload. So this is the hardware enabling confidential computing options. Okay. So then we'll come to the next important part. So confidential computing is a vast area. I just give you a brief idea about what is this confidential computing. So uh, when we discuss about the confidential computing, that there's a problem that comes to your mind. Here we address the fundamental questions. How do you trust a trusted execution environment running on a remote, untrusted machine? You can't physically inspect the hardware, verify the software, or audit the environment. Yet, you need to send sensitive data for processing. So, first challenge: the user send a unique, random nonce to the remote trusted execution environment. This nonce prevent replay attack by ensuring freshness. Each attestation exchange the unique, and then the report generate. The trusted execution hardware generate the cryptographic code containing the nonce, a hash loaded code. We call it as MR enclave, and platform security measurements there. And this code binds the user challenge to the actual trusted execution environment. So in here I'll explain this stepwise. So the challenge: the user send a unique random number to the remote, and this one prevents replay attack by ensuring prevention. And the report generation: the trusted execution hardware generate the report. We call it as a quad, which contain this non received from the user, and the cryptographic hash of the code loaded in this trusted execution environment. We call it as a Mr. Enclave, MR Enclave. Other platform security measurements are there. So this quad binds the user challenge to the actual state of the TE. It's ensure the integrity. And then the third point, signing. So then this code is signed using the private attestation key, unique to the CPU and securely protected in hardware. So this key never leaves the process and cannot be extracted. So the signing and then verification. The user verify the signature using the hardware vendor's public key, and then verify the signature used in public key, ensure this nonce matches the original challenge, and then compare this reported code hash to the trusted application to the expected value. So the finally results only after successful verification does the user trust the trusted execution environment and proceed to send secret or sensitive data. So those are the steps, okay, main steps, but there are a lot of other stuffs also should have to connect with this one. This is the basic idea that I want to give you, the remote attestation part. So we will again do a small stuff before moving on to the next, discuss about the next pillar. So rank these security priorities of your organization. I don't know the detail about the participants. Maybe some of them work in the organization, some of them are students. Anyhow, what do you think in any organization? How are you going to rank the security priorities of your organization? Same stuff. You can scan the QR code, or you can go to the menti.com and share your idea.
Can you please leave the QR code for a couple of minutes on?
Yes, sorry.
Thank you. And I think you may need to update the Mentimeter, because it's still showing the first question about data security.
Yes, I think now. Okay.
Could you please share the QR code for those participants who haven't yet scanned it? Thank you.
Okay, so I hope now I will share the. Okay, so that means most of them select, they rank as first as a data encryptions, regulatory compliance, yes, access control, and audit trail. So most of them rank first as data encryption. Okay, so okay, so now up to this point, we discuss about our first pillar, confidential computing. And now we are going to discuss about the next pillar, that is federated learning. Okay, so that is the revolutionary yeah, research work in the machine learning, in the new work in the federated learning. So federated learning is decentralized approach, decentralized machine learning that allows multiple devices or institutions to collaboratively train or shared model without sharing their raw data. So that's the idea. So this preserve the privacy while still benefiting from combining this data insight. So you can mention examples like smartphones, improving predictive tests, or hospitals Okay, so they are jointly work and train in their medical models. Okay, but without exchange in patients' data, they can model the training models. Okay, so I will explain in here clearly. This slide, you can say this standard. This is a secure federated learning workflow in healthcare scenario. Okay, so this is the central server. So central server send the global model to the each client as the first step. Each client then updates the local model with their local data set. Okay, each client update the model using their local data set and then send the updated model back. Okay, the server aggregates all update and improve the global model. Note that this execution is, you can see that we can create their local models and the global model it updating using local model without exposing, without sending their protected their critical health records. Okay, so that's the idea behind in this federated learning. Okay, actually in here that I'm putting as scenario 1. Now I am going to demonstrate these things. For that, for the confidential computing, I am using the platform called SCORN. Okay, so there are a lot of framework that use for the confidential computing. In here I am using SCORN for Intel SGS machines. Okay, so previously I discussed in the hardware level Intel SGS and the ARM CCA. Likewise, in here I'm using Intel SGS in this Cone platform. And for the Flower federated learning, I'm using Flower. Okay, so likewise, there are also several platforms. In here I'm using Flower. In first scenario, I will run this one without using any confidential computing environment. That means vanilla, without using non-SGS machine, normal machine, the application executing on Intel CPUs without SGS support. Okay, so I hope that all of you can see my demonstration. I will so you can see it's downloading the training data. Okay, and here now in the server it is starting the Flower server and generating, and it's creating their model. Okay, so the server, and there are two clients. Client 1 now connecting to the server, and then they are already started their federated learning training. So in here, and server 1, now you can see in the Flower, this it's 2 rounds, 3 rounds. Yes, again, the same stuff you can see. So this is the simple program using some simple test. Okay, so first, the federated learning is executing in here using one server and the 2 clients. Okay, I will show you then. We'll come to this part later. So now, you can see if I discuss about the federated learning, it's there are there are some we can give some solution for the privacy attacks. Okay, so some integrity, some confidentiality is there, but there are some threats in these federated learning applications. Okay, the first attacker, So you can see these are the some of the security threats, attacks in the context of this federated learning. So normally federated learning means you can identify without exposing the local data, we can train the model. Okay, so some privacy stuff is there, but still there are some threats there. So these are the first, an attacker with privilege or root access on the server or client devices can easily extract training models and compromise in sensitive data. And second, the large number of malicious clients can then they can combine together, combine in their inside to interfere local data set or reconstruct the private data, private informations. And then third one, the malicious client can manipulate this local training data or parameter updates and intentionally corrupted the global model. Okay, so which is known as model poisoning. Okay, so you can see in here model poisoning. So understanding these threats, it helps to appreciate why these architectures that need this confidential computing, why we need to create the confidential federated learning are necessary. So in the federated learning also there are some model poisoning and inference attacks. Okay, so now I will show you when it's combining with the confidential computing how we are going to tackle those problems. So this slide actually emphasizes the gap between the theoretical and the practical implementation. The first program directly against the raw trusted execution environment is highly complex and error prone, and it also demands specialized knowledge that most developers that do not have. Second, this federated learning, okay, so across heterogeneous devices adds another layer of system complexity. So to address these challenges, high level abstraction for confidential computing, that we use this con platform. At the end of the slide said I put the link for this one. Okay, it provides a platform that simplify the development while preserving security guarantees. For federated learning, I'm using this Flower, offers flexible framework to coordinate multiple clients efficiently. Together, these platforms enable us to implement confidential federated learning in a practical and scalable way. Actually, this is demonstrations that we created for the Near Data EU project. Okay, so the Near Data project that we are creating some confidential federated learning platform for uh, that the for the medical data. Okay, so these demonstrations that are used in here used for the Near Data project. Okay, so I will discuss this SCORN again. That's a platform for running unmodified applications containers inside the Intel SGS enclave, and it has some it is a lot of first transparent converter lifts and shift standard Docker containers into the SGS enclave, so developers can continue using familiar workflow lift and shift mechanism. And also attestation and secret management facilities are there. So SCORN automates the remote attestation process and securely provisions the secret directly into the running enclave. It's actually eliminate the manual steps and reducing potential vulnerabilities. So the main benefit is that developers can leverage the strong security guarantees of SGS while keeping their development process simpler and familiar. And Flower in here, I'm using the framework as Flower. So Flower actually it is an open source framework for building federated learning systems. It is a different machine learning libraries. It's work PyTorch and workflow. So this makes it flexible for researchers and developers. Okay, client and server abstraction for the participant logical unit. Okay, so the main benefit is that Flower, it's lets for the researchers, developers focus on designing and experimental in machine learning strategies without worrying about the low level orchestration and communication details between the client and the server. Okay, so those are the two platforms. Okay, so now we will move on to our healthcare domain problem. Okay, so in this slide present the, now think about the previous one, now the federated learning domain, and all the client hospitals are combined together. So there's a research problem, it's coming. How to ensure confidentiality, integrity, and consistency if advisory has root and hardware access. Okay, so this slide present the core research problem in confidential federated learning for healthcare or any other sectors. The challenge is, how do we ensure confidentiality, integrity, and consistency of the federated learning process, that if and this advisory, okay, has a root privilege or even he has a hardware level access. So for that, our approach, so you can see, our approach to address this challenge is to run this application inside the trusted execution environment, TEE. So trusted execution environment is a SGS enclave, and it's create a potential protected area in memory, so where the application can execute securely. So even a root user or compromised operating system actually cannot access the sensitive data or model parameters. So this allows us to preserve this privacy and integrity of this federated learning workflow, even in potentially this holistic environment. Okay, so I will, this is the idea. Now this our local training, okay, and the global training all are running inside the trusted execution environment. That means now we are the hardware mode, we are running in the Intel SGS. Okay, so sorry that the maybe not visible clearly. In here you can see now in here SCON parameters, you can see now it's running inside the SCON Intel SGS platform, client, server, here now it's running inside the Intel SGS. Okay, so now then here if I go back to the this one, you can see this slide actually explain this scenario too. These are some of the docs that I in the slides that I put the link there, you can see in here. So these are the some of the functions, and these are the YML file that we added some SCON features, we enable it. Okay, and then it's running the global model and the local updates are processed equally inside the enclave. So even in the operating system, so malicious user has a root access, they cannot access the sensitive data or model parameters in this way. Okay, so then again another problem, research problem occur after that. is now the federated learning, a large number of malicious clients. Okay, a key challenge is handling in the federated learning. The key challenge is handling these malicious clients. So these clients might be to interfere sensitive information from other participants' local models. So they can tamper with their local data or model updates to corrupt the global model. Okay, so how can we solve this problem? Malicious clients can tamper with their local training data or parameter updates forwarded to the central training system to corrupt the global model. So for that, to address this, in here we use this configuration attestation service. Okay, in this con, it has a configuration attestation service which leverages the remote attestation capabilities of trusted execution environment. So the CARs ensure that only verified and properly configured enclave participants, and providing both confidentiality and integrity of the federated learning process. So even it is an attack has root or hardware access, they cannot compromise the system. For that, we develop these cars. So in here, so the in scenario 3, actually, that we are going to run using Intel SGS with this CAS component, we integrated our configuration and attestation service with the Intel SGS enclaves. Okay, so this is the model. In here you can see training data. Okay, and we call data broker for this CAS component. Okay, so the data broker, the left figure shows the overall system architecture, where these cars verify the configurations and attestations of each one enclave before allowing it to participate in the federated learning. Okay, and the right side, okay, it is policy management within these cars. That means each client and enclaves are allowed to connect, ensuring only trusted components are part of the system. Okay, so this approach protects malicious client and ensure the confidentiality and integrity of this global model. So training data owner, training code owner, model owner, interference code owner. Okay, first attestation and policy submit. Okay, and then after this attestation approve, okay, secret provisioning, they can integrate into that. Okay, so then this is the model and given a solution for the research that problem. Okay, so first I'll give you some idea about what is this CAS. Okay, so the configuration attestation service is a central component. Okay, so it ensures that only verified code runs in the enclave, either via a local attestation or remote attestation. And also CAS also provision configurations securely, and it manage policies. Okay, for manage policies for trusted clients and enclaves, and perform final configurations of the target applications. So this ensure that federated learning tasks executed securely, maintaining confidentiality and integrity even in untrusted environment. So the CAS configuration and attestation services provide these mechanism, and you can see in here maybe this running inside the Intel SGS. So here now we are reading the training data. So in here you can see it is encrypted. Okay, we can't read it, but final attestation process, okay, the data is visible. Okay, local attestation run on the untrusted host, gather the attestation evidences And here you can see central service that manage security policies. So here we attest in the public cars, okay, and private cars also there. In here I'm using the public cars. So calls concessions, configurations, and the secrets. Okay, so we are coming to the maybe. So here, this is our car's address. Okay, again. Okay, so this is the way. Now you can see. Now first I show you the federated learning, how it's work in the demonstration. And then the research problems arise in these privacy issues. And then first, we run in the Intel SGS hardware mode in this con framework. And after that, we integrated with the configuration and attestation service. And I will show you how we are going to solve the problem in the research problem. Okay. So then
Pupitu, we may want to conclude. Sorry for interruption, but we are just out of time now. We may want
yes.
to shortly conclude and take a couple of questions.
Yes. And then another thing that we use for the network shielding also for the this mechanism. Okay, I'm not going to discuss more about this. It is the network shielding means the client and the server that connect in through the network that also shield. Okay, so you can see in here that the untrusted parties cannot address this and that cannot collect the data. Okay, so so that's a closing reflection will come in to the end. The future direction and the open research questions that I want to discuss. Within the 1 hour period, this confidential computing and federated learning is a vast area. Okay, I can't cover everything, but I just want to give you an idea about there are something called confidential computing and the federated learning, and both of them have some issues, but when we combine together, okay, we can create confidential federated learning to handle a lot of privacy and security issues. So there are lots. I think some of them may have some. What are the research opportunities? Immediate research opportunities for this domain. Okay, cross-platform interoperability. So. Confidential federated learning across Intel SGS, AMD SCV, ARM CCA. Okay, so we should have to create this open cross-platform interoperability. So that's a one research area. And performance optimization, how we are going to reduce the trusted execution environment, induce this computational and communication overhead. And edge cloud hybrid, so IoT to cloud, okay, how we can integrate this one. And you may heard about zero trust, okay, verification based model. So those are the some of the immediate research opportunities on this domain. Okay, so these are the some of the uh, recent confidential federated learning research papers and the research project that I'm working in the near data, and this contain that this cone platform and the flower labs that you can get. Okay, so final closing reflection. Okay, I encourage hope that you all can again come to this one. Looking ahead, what is the one breakthrough or change you believe is absolutely necessary for confidential federated learning to become the global standard for secure distributed AI, and why? Okay, share your insights through this test. At the same time, we can go to the question and answer sessions as well.
Thank you. Indeed, it's a very vast topic, and to summarize it in 1 hour, it's quite challenging, we have seen. So we have a question from Daniel Peters.
Am I audible?
Yes, you are.
Excellent. Professor Prabhu, do you have a slide showing the references for the citations you made? That wasn't presented. Can you show that?
Okay, sure.
And then while that's taking place, question for you, how are updates? Software gets updated, who knows what schedule. but that, of course, would be identical to a software that has been attacked. How do you recertify, or how does the data provider assure that the software update is not a malicious, but is in fact authorized and secure?
Yeah, so that's why I'm explaining about that. For that scenario, we should have to do some attestation process. So the local attestation and remote attestation process is going there to check whether that it has a trusted party.
And then you had numbered citations. Is this the slide that there's no numbers on this slide?
Okay, sorry, I will update it.
Okay, thank you.
I will share my email address. If there are anything, then I can contact them and send more details.
Thank you. And since we are already beyond the scheduled time, and it appears there are no more questions, I would suggest that we close the session now. And just for your information, the recording as well as the slides will be available. The link will be sent to all the participants. Thank you very much, everyone, for joining. Have a nice evening.
Okay, bye.